Hi everyone. Today we will discuss some important points from statistical thermodynamics. Okay. So what are the points you have to focus from statistical thermodynamics? Okay, this video we are taking to benefit TSNCO aspirants. Okay, statistical thermodynamics. Statistical thermodynamics deals with what? The name itself indicates it gives correlation between quantum chemistry and thermodynamics. It is the application of statistical mechanics to thermodynamics. It gives relation between quantum chemistry and thermodynamics. It gives correlation between microscopic properties and macroscopic properties. Okay, it gives correlation between microscopic properties and macroscopic properties. For example, from quantum chemistry we'll get what are the various possible energy levels for a given system. What are the various possible energy levels for a given system? If you take large number of molecules in the system, how those large number of molecules are distributing in various possible energy levels, that we can study under statistical thermodynamics. Okay, what are the various possible energy levels we can get from quantum chemistry? Okay, we are taking large number of molecules. How these molecules are distributing among various possible energy levels, that we can study under statistical thermodynamics by using concept of distribution. By using concept of distribution, probability and partition function. This concept is important, partition function. This partition function gives relation between quantum chemistry and thermodynamics. So partition function gives relation between microscopic properties and macroscopic properties. Okay, in this, first of all, you have to concentrate on ensemble and different types of ensembles. First of all, what do you mean by ensemble? If you have a collection of particles, each particle is called a system in statistical thermodynamics, and a collection of systems is called assembly. Okay, each particle is called as what? System. Collection of particles is called what? Assembly. And a collection of assemblies is called ensemble. This is called what? Ensemble. Collection of imagined identical assemblies. Collection of imagined identical assemblies is called ensemble. Identical in the sense, okay, each assembly is characterized by some same properties, and each assembly is characterized by some same properties. Okay, what are the same properties possessed by each assembly? On that basis, ensembles are classified into 4 types. Okay, each particle is called system, collection of particles assembly, collection of assemblies is called ensemble. Each assembly is characterized by some same properties. Based on that, we have 4 types of ensembles. Okay, first one, uniform ensemble. Uniform ensemble. If the density of each assembly is same, if density is constant, then such ensemble is called uniform ensemble. Okay, volume is same, and volume of each assembly is same in each case. Volume of each assembly is same in each case. If the number of particles are also same in each assembly, then what about density of each assembly is same? If the density is same, then such ensemble is called uniform ensemble. Next one, canonical ensemble. So no need to much think about these ensemble concept, and just you remember these conditions. Canonical ensemble. This is similar to closed system in thermodynamics. This is similar to closed system in thermodynamics. We know in closed system, no exchange of matter, but exchange of heat takes place. No exchange of matter, but exchange of heat takes place. In this case also, in between two assemblies, no exchange of matter, but exchange of heat takes place. Okay, exchange of heat takes place to maintain constant temperature. So each assembly is characterized by what? Constant temperature, constant volume, and as no exchange of matter, number of particles in each assembly remains the same. as no exchange of matter, number of particles in each assembly remains the same. So if TVN remains the same, such ensemble is called a canonical ensemble. So if you take two assemblies and two assemblies are separated by what? Conducting wall. As there is exchange of heat, two assemblies, two adjacent assemblies are separated by what? Conducting walls and impermeable walls. Impermeable comma conducting walls. Impermeable means there is no exchange of matter. Conducting walls means there is exchange of heat. And okay, if TVN remains the same, that is called canonical ensemble. Next one, microcanonical ensemble. Microcanonical ensemble. This is similar to isolated system in thermodynamics. And we know in the case of isolated system, no exchange of matter and no exchange of heat. That means each assembly is separated from adjacent assembly by what? Impermeable and non-conducting wall. Impermeable and non-conducting wall. As there is no exchange of matter, N remains constant. As there is no exchange of heat, energy remains constant, and volume is common. And volume is common in each case. So if EVN remains the same, each assembly is characterized by same EVN values, then that is called microcanonical ensemble. And last one, grand canonical ensemble. Grand canonical ensemble. This is similar to open system in thermodynamics. Open system means exchange of matter takes place, exchange of heat also takes place between system and surroundings. So here exchange of matter takes place to maintain constant chemical potential. Exchange of heat takes place to maintain constant temperature, and volume is common in each case. Okay, so you may remember like this grand open. So grand canonical ensemble is similar to what? Open system, which remains constant, and each assembly is characterized by same T, V, mu, and each assembly is separated from other assemblies by what? Permeable comma conducting walls. Permeable comma conducting walls. Okay, so just you remember these points. And uniform ensemble means density remains same. Canonical means TVN. Microcanonical EVN remains same, and grand canonical means TV mu remains same. Okay, this is the concept of ensemble. And okay, next one, probability. Probability means what? Probability is equal to weight of a particular configuration by total weight, or the number of ways of arranging a particular configuration by total number of ways of arranging the particles. So that is called probability. Always sum of the probabilities is equal to how much? 1. For example, if you toss a coin, the probability for getting head is 1 by 2. The probability for getting tail also 1 by 2. So 0.5 plus 0.5, 1. So always total probability is equal to how much? 1. So probability of a particular configuration is equal to what? The number of ways of achieving that configuration by total number of possible arrangements. That is the probability. Next one, types of statistics. And types of statistics. We have 3 types of statistics. The first one is Maxwell-Boltzmann statistics. We have 3 types of statistics: Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. In that mainly you concentrate on Maxwell-Boltzmann statistics, important, and Maxwell-Boltzmann statistics. So in this statistics, what are the assumptions? If you see, the particles are considered as distinguishable. The particles are considered as distinguishable. For example, if you take particles A, B, C, and so on, whether these are distinguishable or not, yes, these are distinguishable. For example, if you take all the particles like this, A, the particles are said to be what? Indistinguishable. So in this statistics, the particles are said to be distinguishable. And in a given energy level, any number of particles may present. Any number of particles can present in a given energy level. There is no any restriction on the number of particles to be present in a given energy level. Any number of particles may present in a given energy level. The particles which follow this statistics, those are called Maxwellians or Boltzmanns. The particles which follow this type of statistics are called Maxwellians or Boltzmanns. Okay, according to this statistics, okay, for example, we have L number of energy levels and L number of energy levels, and N is the number of particles to be distributed among L energy levels and L is the number of particles to be distributed in L energy levels. Then the number of ways of arranging the particles is L power n. The number of ways of arranging the particles is L power n. For example, we have two energy levels and two particles and two energy levels, two particles. In how many ways we can arrange? Four ways we can arrange two particles and that is A, B, B, A. Both may present in a given energy level. There is no restriction on the number of particles. So these are the four ways we can arrange it. So the formula for W is L power n. For example, if G is the number of degenerate energy levels present and N is the number of particles we have to distribute, what is the number of ways of arranging the particles? In how many ways we can distribute N number of particles in G degenerate energy levels, and same and G power n. Just in the place of L we will get G. The difference is, for example, two particles we have, okay, two degenerate energy levels we have. Two particles, two degenerate energy levels. In how many ways we can arrange the particles? And in four ways. So see here, these are the four ways we can arrange. Okay, these two are degenerate energy levels. And these two are degenerate energy levels. A, B, B, A comma B, A comma B. So these are the four ways we can arrange. And okay, so right, G is the number of degenerate energy levels and N is the number of particles to be distributed. The formula is how many ways we can arrange G power n ways we can arrange the particles. And sometimes previously the question given like this, and we have three types of colored balls, and two boxes we have. In how many ways we can distribute? And okay, the number of balls are 3, the number of particles are 3 colored balls, and so distinguishable balls we are taking, and the number of boxes are 2. So the number of ways of arranging 3 colored balls in 2 boxes are 2 power 3, that is in 8 ways we can arrange it. Okay, next one, the third case is, for example, we have various energy levels like this, and E1, E2, E3, like this we have various energy levels. N1, N2, N3 is the number of particles present in the given energy level. N1, N2, N3 is the number of particles present in the energy level. Capital N is the total number of particles, that is N1 plus N2 plus so on. That is the total number of particles. Then in how many ways we can arrange the, okay, N1 particles in E1 level, N2 particles in E2 level, N3 particles in E3 level, and so on. The formula for that is W is equal to N factorial by pi Ni factorial. Pi means what? Product, and pi means product. Sigma means summation. Okay. For example, I am taking total number of particles 2, and that is A comma B, distinguishable particles I am taking. We want to distribute, I am taking 3 particles and A, B, C. We want to distribute in 2 energy levels, E1 and E2 energy levels, such that occupation number of E1 level is 1 and occupation number of E2 level is 2. And for example, we are taking like this, occupation number of E1 level is 1, occupation number of E2 level is 2. The 3 particles are distributing like this, and so in how many ways we can distribute? And the formula is what? W is equal to N factorial. What is the total number of particles? 3 factorial by N1 factorial, that is 1 factorial, pi means product, and into N2 factorial, that is 2 factorial. So 3 factorial means what? 3 into 2 into 1, 6, 2 into 1, 6 by 2. That means in how many ways we can arrange it? In 3 ways we can arrange it. The number of ways of arranging the particles is 3. Okay, N1 1, and so first time I am placing in E1 level A, in E2 level B comma C, next B A comma C, next C A comma B. So these are the 3 possible arrangements we have. Okay, we are distributing 3 distinguishable particles in 2 energy levels such that occupation number of E1 level is 1, occupation number of E2 level is 2. Then what is the number of possible arrangements? What is the number of microstates? What is the number of ways of arranging the particles? Okay, W means number of ways of arranging the particles, or number of possible arrangements, or number of microstates, and that is 3. And like this we can calculate it. Next is, sometimes they may give like this, and here we are taking all our non-degenerate energy levels. We are taking all our non-degenerate energy levels. For example, we have more than one degenerate energy levels. We have degenerate energy levels like this. Occupation number of this level is 1. Occupation number of this level is 2. Occupation number of this level is 3. Okay, we want to distribute the particles like this: N1 in E1 level, N2 in E2 level, N3 in E3 level. Degeneracy of first level G1, degeneracy of second level G2, degeneracy of third level is G3. Then what is the number of possible arrangements or number of microstates? The formula is pi into Gi power Ni by Ni factorial. So extra what we are getting, Gi power Ni, and the second case Gi power Ni we have. Here we considered only one degenerate energy level. Here we have more than one degenerate energy levels. So we have to apply the same concept to all the energy levels. And pi means we will get product, and G1 power N1, G2 power N1, so on. Here N1 factorial into N2 factorial into so on. Okay. For example, we have like this, and G1 is 2, G2 is also 2. Number of particles are 3, A, B, C. Okay. N1 level, E1 level 2 particles we want to distribute. E2 level 1 particle we want to distribute. What is the number of possible arrangements? W is equal to what we have, N factorial, that is 3 factorial into G1 power N1. G1, what is the order of degeneracy of first level, and 2. 2 power N1, N1 value is 2. Next G2 power N2, that is 2 power 1 by N1 into N1 factorial, 2 factorial, N2 factorial, that is 1 factorial. Okay. So 3 factorial means what? 3 into 2 into 1, that is 6. Next to 2 gets cancelled. 6 into 4, 24. And so the number of possible arrangements are 24. So these are the 4 possibilities we have. Okay. If you take distinguishable particles, how to distribute them in various possible energy levels? Okay, that for that we have 4 formulas and 4 cases we have according to Maxwell-Boltzmann statistics. Okay, L energy levels we have, N particles we have. There is no restriction on the number of particles, and in this case no restriction on the number of particles. The number of ways of arranging the particles is L power N. If G is the number of degenerate energy levels and N is the number of particles to be distributed, and no restriction on the number of particles present in a given energy level, then W is equal to G power N. Next, third, fourth case, we are giving some restriction, and only N1 particles to be present in E1 level, only N2 particles present in E2 level, like that we are taking. But all are non-degenerate energy levels, this is the formula. If more than one degenerate energy level is there, this is the formula we have. Okay. Next, some other points regarding Maxwell-Boltzmann statistics. According to Maxwell-Boltzmann statistics, what is the expression for number of particles present in a given energy level? Number of particles present in ith energy levels. The formula is e power minus alpha minus beta ei, or we can write as 1 by e power alpha plus beta ei. Okay, this is the formula for number of particles present in ith energy level. Alpha and beta are constants. Alpha and beta are constants. Or we can write it as Ni is proportional to e power minus beta ei, as alpha is constant. So e power minus beta ei is called as Boltzmann factor, and e power minus beta ei is called as Boltzmann factor, and the expression for beta is 1 by kt. So therefore Ni is proportional to e power minus ei by kt. This is the expression for population present in ith energy level according to Maxwell-Boltzmann statistics. Okay. So according to this, at a given temperature, at a given thermal equilibrium, at a given temperature, at a given thermal equilibrium, as energy increases, what about population? Decreases exponentially. As energy increases, population decreases. Always higher energy levels possess less population compared to lower energy levels. Okay, that you remember. As energy increases, population decreases. Okay. So next one, what is the expression for fraction of particles present in ith energy level, fraction of particles present in ith energy level, or probability for finding the particles in ith energy level. Fraction of particles present in ith energy level or probability for finding the particles in ith energy level is given by e power minus beta ei by n means what? Summation I ni. N means what? Summation I ni. So summation I e power minus beta ei. Beta we can write as 1 by kt. This is without degeneracy, and this is without degeneracy. If there was a degeneracy, this is the formula, and gi into e power minus beta ei by summation I gi e power minus beta ei. So you better to remember this equation, and since there was no degenerate energy levels, g value is equal to 1. Order of degeneracy is 1. No degenerate energy levels means non-degenerate energy levels means what? G value is equal to 1. And okay, so this is the expression for fraction of particles present in ith energy level. Based on Maxwell-Boltzmann statistics, if you have two energy levels, and Ni and Nj energy level, sorry, Ei and Ej levels, the populations are Ni and Nj. And okay, now the gap between these two energy levels is delta E. We have two energy levels, Ei and Ej. The populations are Ni and Nj. The gap between those two energy levels is delta E. Okay, now how to give relative population, and how to give relative population Nj by Ni. So this relative population is useful in spectroscopy also to compare intensity of spectral lines, and some transitions are occurring from Ei level, some transitions are occurring from Ej level, okay, whose intensity is high, and okay, the corresponding spectral lines intensity is high, whose corresponding spectral lines intensity is high. That depends on what? Population. And if Ei level population is high, its intensity is high. Okay, so therefore this is useful to compare what? Intensity of spectral lines, and so we can give relative composition also based on Maxwell-Boltzmann statistics, and so according to this we will get, if you apply this equation, and Ni is proportional to e power minus Ei by kt, or Ni is proportional to e power minus beta Ei, we'll get Gj by Gi into e power minus Ej by kt by e power minus Ei by kt. If you bring that to numerator, we will get e power minus delta E by kt, and delta E is the gap between those two energy levels. So this is the expression for relative population. This is about Maxwell-Boltzmann statistics, and these are some points you have to remember based on Maxwell-Boltzmann statistics. Okay. Next one, Bose-Einstein statistics. Relatively, Maxwell-Boltzmann statistics important, and so I will give some points regarding Bose-Einstein statistics. What about the assumptions in the Bose-Einstein statistics? In this, the particles are assumed as indistinguishable, and the particles are considered as indistinguishable. For example, if you take all the particles are of the same material, all the particles are of the same material, then particles are what? Indistinguishable. And here also there is no restriction. Any number of particles can occupy a given energy level. Any number of particles can occupy a given energy level. The particles which follow this statistics, they are called as bosons. The particles which follow the statistics, they are called as bosons only. The particles having integral spin follow this type of statistics. The particles having integral spin follows this type of statistics. The examples you may remember: H2, N2, D2, helium-4 and photons. These are some examples for the particles which have integral spin, so they follow Bose-Einstein statistics, and they possess symmetric wave functions. And bosons possess what? Symmetric wave functions. Symmetric wave functions means if you exchange the electrons, is there any change in the sign of the wave function or no change in the sign of the wave function? If you exchange the electrons, if there is no change in the sign of the wave function, that is called symmetric wave function. For example, psi is equal to, if you have 1s of 1, 1s of 2, and now if you exchange the electrons, and 1s of 2, 1s of 1, I am exchanging the electrons. Okay, now we are getting same function or different function? Same function we are getting. So no change in the sign of the wave function. That is called symmetric wave functions. and symmetric wave functions do not follow Pauli's principle andi. So they do not follow Pauli's principle, that we will get in quantum chemistry, and just you remember that. Okay, this is about Bose-Einstein statistics andi. Particles are indistinguishable. Any number of particles can occupy a given energy level. The examples are particles having integral spin. They are called as bosons, and they possess symmetric wave functions. Okay, as they possess symmetric wave functions, they do not follow Pauli's principle. And the examples for number of particles present in ith energy level, the expression 1 by e power alpha plus beta ei for Maxwell-Boltzmann statistics minus 1 we will get, and according to Bose-Einstein statistics. That is the expression for number of particles present in ith energy level. The third one is Fermi-Dirac statistics. And third one is Fermi-Dirac statistics. In this also the particles are said to be indistinguishable, but only one particle can occupy a given energy level. Only one particle can occupy a given energy level. The particles which follow this type of statistics, they are called as fermions. The particles which follow this type of statistics, they are said to be fermions only. The particles having half integral spin follows this type of statistics. The particles having half integral spin, those particles follow this type of statistics. The examples are electron, proton, neutron, helium-3 and NO. These are some examples where the particles possess half integral spin. So they are said to be what? Fermions. And fermions possess anti-symmetric wave functions. Fermions possess anti-symmetric wave functions. That means psi of 1, 2 is equal to minus psi of 2, 1. If you exchange the electrons, what happens to the sign of the wave function? Changes. And if you exchange the electrons, sign of the wave function changes. For example, if you have like this, and if you exchange the electrons, what we will get? Negative we will get. Negative of this one we will get if you exchange the electrons. So fermions possess which type of wave function? Anti-symmetric wave function. According to Pauli's principle, the wave function should be anti-symmetric. That means these fermions follows what? Pauli's principle. Fermions follows what? Pauli's principle. And these are the three types of statistics we have. Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. Right. Next one, this one you may remember one thing, Stirling's approximation. And Stirling's approximation, ln n factorial is equal to n ln n minus n. And ln n factorial is equal to n ln n minus n. This is useful when we want to simplify ln large number factorial. And ln large number factorial. To simplify ln large number factorial, it is difficult to calculate. And for example, if you take Avogadro number 10 power 23 factorial, it is difficult to calculate. Instead of calculating 10 power 23 factorial, what we will do? 10 power 23 ln 10 power 23 minus n we can calculate 10 power 23. So that is somewhat easy to calculate. Next one, what is the condition for most probable distribution or dominant configuration? This is the formula. 1 plus ln ni dni is equal to 0, or we can write this as summation I ln ni dni is equal to 0. This is the condition for what? Most probable distribution or dominant configuration. Okay, these are the various configurations we are taking. Various possible arrangements we are taking. Okay, various possible arrangements we are taking. So we are taking probability. So the configuration with the most probability, and this is called what? Dominant configuration. This is called dominant configuration. Okay, or whenever particles are distributed evenly, that is said to be dominant configuration. Whenever the particles are distributed evenly, that is said to be dominant configuration. This is the formula for dominant configuration. Even distribution, and even distribution means, for example, we have three energy levels, and E1, E2, E3. we have 6 particles and so what is the 6 particles and what is the dominant configuration and so we can distribute these 6 particles like this and 510 420 321 okay 222 like this. In various ways we can distribute it. This is one configuration, this is one configuration, this is one configuration, this is one configuration. In this, what is the most dominant configuration where the particles are distributed evenly? That is the dominant configuration and 2 2 2, that is the most dominant configuration. For this, more number of possibilities we will get. For this we will get more number of possibilities and okay, the possibilities are what? N factorial, that is 6 factorial by 2 factorial, n1 factorial into n2 factorial into n3 factorial. Like that we have to simplify and that is the, in this case we will get more number of possibilities and so what is the most probable energy and most probable energy is what? 2 particles in E1 level, so 2E1, 2 particles in E2 level, 2E2, 2 particles in E3 level, so 2E3. So this is the most probable energy of the given system and that is the most probable energy of the given system. Okay, this is the number of possibilities and like for dominant configuration. So next one, what is the relation between entropy and probability? So the relation is, just you remember, S is equal to KB ln W or K ln W. W is the number of microstates or number of possible distribution or number of possible arrangements and KB is Boltzmann constant. Okay, KB is nothing but what? R by N. Gas constant for one molecule is called Boltzmann constant. So S is equal to KB ln W and here based on the data given, W we can use as L power N or G power N. 4 possibilities we discussed previously. N factorial by pi Ni factorial. Based on the data given we have to follow N factorial into pi into Gi power Ni by Ni factorial. These are the 4 cases we discussed. W, KB ln W and okay. Based on the data given we have to use these expressions and or another one is 2j plus 1 and sometimes they are giving term symbol and term symbol, you know, term symbol Lj 2s plus 1. What is the formula for number of microstates and 2j plus 1 is the formula for number of microstates. So if the term symbol is given, W we have to take as what? 2j plus 1 and okay, right. This is the relation between entropy and probability. Okay, so next we have to discuss partition function and right, that we'll see in the next class. Thank you.